Oh, I'm pretty sure they do. You ever been in someone's house and they don't change their fire detector? Yeah, smart. Oh, yeah, yeah. It's ridiculous.
So I'm telling him, I'm like, you don't hear this? And he's like, absolutely.
Yeah, that's you know what's why? You didn't know that was like a thing?
Well, I knew it.
Yeah. Oh, no, that's nothing. That's, that's not the norm. Yeah. Oh, yes, we didn't understand. It's a big pet peeve of mine. Go walk into someone's house. Like, I would literally go buy you a nine, go back, and I would change for you. Just because, yeah, I feel like it's necessary.
Being her, I did it. Like I was talking.
Mm.
I was at his house last week with ice.
I would change mine almost instantly. The batteries are a little expensive. And they're like $3 a piece. But we spend waste money on worse. Oh, for one battery, $3. You know, it can, yeah, you just put the card in and just get it. Yeah. Oh, how's the house hunt? Or have you moved into your house yet? Oh, no. Oh, being built. Oh, yeah. Oh, that's fun. Yeah, I had. Are you living with relatives? Oh, um, oh yeah. Yeah, that could be stressful. I had to move back with my mom. Yeah, living with my mom as an adult. So it's literally it's different. All right. So what we're gonna do today, we are going to finish. Since you all weren't here Monday, I believe I recorded that lecture, so I'll go ahead and post that via Zoom. So I think I recorded that. So you can go back and look at that. Okay. Um, so we're gonna move forward. I'm gonna go over the example that we did, and then we're going to move into the next chapter, not chapter, section. Okay. So let's do this again so that you can kind of get a feeling for where we are. Where is an example that I used? Where is that example that for English writing? Let's do this. All right. We're gonna do this one. And then we'll, yeah, let's do this. All right. Here's our example. So, here's the example. It says a local researcher decided to test the result of and here's research wearing red as being more attractive than when they were wearing other colors. Wrong color.
I find that when you ask men what their favorite color is,
Yep.
they have two answers.
Yep.
Red, blue, and if they're interesting people, they're gonna say purple and green. But
my taste in colors has changed. Because I used to be blue, black. Now I can wear greens. I like greens and blues, yellows. Yeah, but I didn't wear it. I used to wear grays, blacks, and blues. Okay. So that's a research question. So it says, based on these results, researchers reasoned that the same phenomenon might influence the way men react to waitresses wearing red. So what they wanted to see is if a waitress wore red versus any other color, how much would they be tipped? Right? So if a waitress is wearing red, would they be tipped more than the same waitress wearing, say, a blue or green shirt? Okay, so that is the research. So they had in their study waitresses wear in 5 different restaurants wore T-shirt in 6 different colors: red, blue, green, yellow, black, and white. They wore on different days of the week for a 6-week period. Okay, it says except for the T-shirts, the waitresses were instructed to act normally and report each customer's gender and how much they left as a tip. The results show that male customers gave significantly bigger tips to waitresses wearing red, but that color had no effect on tipping for female customers. So females don't care what people wear. Okay. It says the researcher decided to test this result by repeating the basic study at a local restaurant. Waitresses at the restaurant will routinely wear white shirts, black pants, and the restaurant records records indicate that waitresses' tips from male customers average 16% of the bill with a standard deviation of 3. Okay, so the population is going to be 16%, and then the standard deviation is going to be 3% plus or minus. Okay, so that is the first. So this is 16% of the bill. So if my bill is $10, then I'm going to tip 160. Okay, all right, that's the average. That's when they wore only white. Okay, so this is the population. All right, so when they decide to run their study, let's see what they say. Okay, so it says, on the other hand, if the sample is still around, so it says if the mean tip, right? What they did is they sampled 36 different people. All right, so the N is 36 male customers. So in this sample, in an experiment with N equals 36 males. So that's our sample. Okay. The 36 males were then, they averaged their tips based on the female wearing a red shirt or any other color of the shirt, right? So during the study, waitresses are asked to wear red shirts, and the researcher plans to record tips for these 36 men. Okay. If the mean tip for the sample is noticeably different than the baseline, which is 16, then we can determine that wearing a red shirt makes a difference in tipping for men. All right. So here is the experiment. Okay. So our null hypothesis is our first hypothesis. So our first hypothesis would be what? Null hypothesis is that there is no change, there is no difference between population and the sample. So what would my null hypothesis be? Exactly. The red shirt has no effect. So we say that the mean, say red shirt, equals 16. Okay. That is the null hypothesis. That's saying that there is no difference, there's no effect with the red and wearing red shirt. All right. The research hypothesis, H1, our alternative hypothesis, would be what? The opposite. So it's that the mean for the red shirt does not. Okay? So that's my research hypothesis. So that means with a red shirt, that the mean tip would be either greater than or less than 16. So there is a difference. Okay? There is a difference. All right. So given the information, given that information, we're going to, let me find the example. We're going to start. All right. Our second step is I have to set my criteria. Okay. Setting my criteria means I'm going to select my alpha level or my significance level. Okay. My significance level was what choose a two-tailed test. I'm going to say I'm a 5% significance level. Given that information, given it's a two-tailed test and it's a 5% significance level, we'll call this significance, SIG level. I know that my Z-score, or my cutoffs, are plus, let's say Z equals plus or minus 1.96. Okay? So those are my cutoffs for democracy significance level 1.96. And the graph should look something like this, the distribution. Okay? So we'll have a negative 1.96 here, positive 1.96 here. And these are my shaded regions, the outside. And so if this is a 5% total, that means there's 2.5% here. And there's 2.5% right there. Okay. So again, that is my critical region. Those are my critical regions. All right. So for our example, since we know our hypotheses, we know our criteria. Now we need to compute our statistics. All right. So in our example, in our study, it says that for the example we may consider, suppose the sample produced a mean tip of 17.2%. Okay, so that means they're tipping 17.2% of the bill, right? So now my mean for 3, keep my statistic. My mean in this case is 17.2. Okay, 17.2. I need to compute my statistics. So the first thing I have to do now is I need to compute my standard error of the mean. Standard error of the mean formula is this. Okay. Okay. So what would be my standard error of the mean? Population 3, standard deviation 3, divided by the square root of 36. Everybody seeing where I'm getting this number? Okay. So that's going to be 3 over the square root of 36 is 6. Good. So I get a positive 0.5. All right. That is my standard error of the mean. Given that this is the standard error of the mean, it's a small standard error of the mean, that's a good thing. That means there's a lack of or a lower variability amongst scores. All right. That is my standard error of the mean. What's the next thing? We have to find our Z-score. All right. So my Z equation is mean, sample mean minus population mean, all over standard error of the mean. Okay. So I plug those numbers in. I have my sample mean here, which is 17.2. Minus 16 divided by 0.5. Standard error of the mean. Okay. So we get 1.2 divided by 2, and we get 2.4 plus 2.40. Okay. Given that information, now step 4 is make a decision. Make a decision. So given my criteria, that I set and my Z-score that I got from my sample, what decision would I make? And I don't think you all were here for this, but let me be word. So you either reject the null hypothesis, which says that there is a difference. Rejecting the null hypothesis means that, yeah, I cross out that there is the same and that there is a difference, or I fail to reject the null hypothesis. Failing to reject the null hypothesis means that I accept it, meaning that there is no difference. Okay. Question? What's that? Yeah, what would we say? You would reject the null hypothesis, right? Because this 2.4 falls in this critical region here. So you could say that 2.4 is somewhere out here. And since 2.4 falls in that shaded region, that means you reject no hypothesis. So you just say reject H 0. Okay. Questions about that? So this is your criteria. This is the criteria you use. So we have three different significance levels that we can use as research. Okay. You have what we call a 5% significance level. You have 1% significance level. You have 0.01 significance level. These significance levels are the probability of, again, rejecting the null hypothesis. All right. Go ahead.
We have like, well, the problem was like, figure out what, so we have to.
You have no steps. Yeah, you have no steps. You'll be given this information.
Okay.
They'll say, I want you to run a two-tailed test, 5% significance. And since you know that information, you already know that if it's 5% significance level is two-tailed, you'll know that the Z-score cutoff is 1.96. And you could, yes. Yeah. But these are just arbitrary. So these are different. So the Z for this one would be plus or minus 1.96. The 1% would be, I think it's 2.58 plus or minus 2.58. What you got? Let me show you. I'm gonna show you on this. You go back. So these are the significance levels. So you'll either have a researcher. So as researchers, we have the ability to select our 1% is 3.30. You would choose these based on your sample size. There are several factors in why we choose certain significance levels. If I have a higher sample size, I know that I know that my standard error of the mean is going to be lower, right? I have a good feeling that if this mean difference is high enough, I know that I would get something that's significant, right? So even if I did, so say instead of doing 1% significance level, I did a 5% significance level, I did a 1% significance level. Then my critical region goes from 1.96 to 2.58. Right? So then what would I do? You fail to reject, right? Yeah, it was 2.58. So then let's do this. I'm going to increase this to 100 men. Increase this to 100 men and see what happens. Okay? So now all I'm doing is changing numbers. So instead of this being 36 now, this will be 100. This should be what, 10? This should be 0.3. Okay. So then this should be 0.3. This should be 0.3. And then our numbers will change. Z towards 4. So now I could have set my significance level at 0.01%, and I still would have rejected. So just by changing the sample size, I changed the whole result of the test. And so that's a really big determining factor. So if I know that I can get a bigger sample size, I might reduce my significance level. So this hypothesis, will there be a difference between the number of 16 men and what they rate or not? Okay, I'm just making a prediction. There's two predictions. One of the predictions is saying that there won't be a difference. The other prediction is saying that there will. Now, the thing that is related to the 100 men is the 17.2. Out of the 100 men, they averaged a 17.2% tip. That they cared about. When they were shown the shirt, this is what they tipped. The original population, they usually wear black top, white shirt, white top, black pants. That's the 16.
Working with the bigger population.
Well, it might. It might. Think about if this had been maybe just 16 and a half. Then this would have been a half, right? So if this would have been 16 and a half, this would have been a half divided by 0.3 as well. No, just do, so this would be 16.5. Just subtract 16 from 16.5 and get a half. It's a half.
1.6.
1.6 repeated.
So if yards accepting are 8.
Yeah, you will fail to reject. Yep. Yep. So by changing this difference, you're changing the results of the test. So you can change it by increasing your sample size or by the effect that you see in the numerator. Okay? Those are very, very important. Now, questions? Any other questions about that? We're going to use this to talk about our next. Okay? Let me. So that's a two-tail test. Two-tail test. The two-tail test gives you an opportunity to see a difference in any direction. Greater than or less than. Okay. However, there are some instances where we use a one-tailed test, and a one-tailed test is a directional test. It is going to give the researcher an opportunity to predict in which direction will the increase or will it be a decrease. So, for example, in this particular example, okay, so instead of doing a two-tailed test, if I wanted to do a one-tailed, I'm going to change everything back to 36. This should be 36. So now I have a one-tail test and 5% significance level. A one-tail test and a 5% significance level means that I have 5% in one tail. So it's in one tail. So instead of it being divided in two, we're just using one. So I'll redraw it. So now you have standard normal distribution, and we are predicting that the amount of tips is going to be greater than the 16. So then I'm going to use everything to the right. So my shaded region will be over here. Okay. So now the z-score is going to be plus or minus 1.65 for a one-tail test. Okay. For a one-tail test is 1.65. Let me go. Okay. With it being a one-tail test, now I'm just checking for anything that falls into this group. Okay. And so given my information we already did, our z-score, everything remains the same. All of the processes remain the same. This is the only thing that changes, right? So if this is a one-tail test, it's going to be plus 1.65. Okay. And if that's a plus 1.65, what is the result? What decision do I make? Exactly, no hypothesis. Because the 2.4 also falls in that shaded. Okay. So what it does with a one-tail test, it increases the likelihood that you're going to reject the no hypothesis. Okay. It increases the likelihood that you will. Two-tail test reduces the likelihood. One-tail test increases the likelihood that you're going to reject. Because even if I reduce, say I reduce that 7.2, actually I'm having to do it. I'll do everything else up. Everything else will remain the same. The only difference is going to be that's the only difference. So now instead of the difference being 1.2, now solve that with a formula. I always get friends. Who is that? Aries. Yeah. Why is that? What would you say that?
But they feel all of the conversation.
Yeah, I can do that. I did a personality test, and I consider myself an introvert. But after taking the personality test, I'm like 75% extrovert. But I'm more of an introvert. It was a big 5-factor personality test. So it was like 120 statements. I sent it. I'm having my fiance do it so we can kind of talk about what our personality made first. Taurus? Yes. I don't know. So yes. Yeah. What did y'all get? 3.9. Okay. Wait. All right. What's the decision? Because even with that, even reducing the size of the effect up top, you still get 1.8. All that critical reason. Okay. And it's for one test. It falls in this region, fail to reject the null hypothesis. They say fail to reject or just accept the null hypothesis. But the more accurate way to describe it would be fail to reject. Simply because with hypotheses, they're just predictions. There's a lot of uncertainty when we're doing research like this and these tests. So I don't like accepting anything because if I did the study again with, again, a higher sample size, it might change it. Yeah, it might change the results. Okay. All right. Questions about that? It's one tail test. Very, very easy. We'll likely just on a test, we'll get two tail tests. But yeah, this is the 1.65. Okay, this is exactly what we did here.
Is that like how two tail tests is multiple 5%, 1%, 0.0. It only has
Yeah.
it has all.
Yeah. If you go, I don't think I have it. But if you go to your sheet, you should be able to find. So if you go to, you're looking for proportion of the tail, and you're looking for 5%. So you're gonna go all the way to 5%. Should be 1.65. There you go. Yeah, so 0.495 is 1%. So that's 5%. If you go down to 1%, let's see what 1% is. It's gonna be one. That should be 2.33. Is a one tail test. That's a 1%, 2.33. So you can use this to find out what your. So if I go 5% two tail. So I know it's two tails, so it's going to be 2.5%. So then you go, should be 1.96. So you should get 2.5. Yep, 2.5 or 0.025. Okay. That's a good question. Any questions about that? Okay. Any questions? Any questions? All right. So given this information, knowing that we can reject the null hypothesis is important, right? But the next step to that, and in every piece of research that we do, is to understand what our effect size is. Right? Effect size is how we determine what the magnitude of these differences are, right? So 16.9 minus 16 gives me 0.9 difference, right? Percentage point difference, right? But what is that magnitude, right? What is the magnitude of? We know there is a difference, but how big is that difference? And the Cohen's d is a measure of effect size that tells me in a standardized way how large and how big that magnitude of that peak effect is. Okay? And so you're going to make this. And one reason this is a standardized measure is it does not take into account your sample size. We saw how sample size plays a big role in significance of a test, but we want to take it out of the equation. All right. So I'll show you what the equation is, and on an exam, you may or may not, or you may. Size measures the absolute magnitude of the change. Even if I failed to reject the hypothesis that said that there was no difference, I still could have a pretty large effect size. Okay? So effect size takes into account, it doesn't take into account the sample size, it takes into account the magnitude difference. All right. So for this example, so we got 16.9, we'll use 16.9. Okay. All right. Cohen's D, that's the effect size measure. Cohen's D is the effect size measure. Here is the formula for Cohen's D. Now good? But knowing the biggest one is that third book, or the second. Effect size measure is absolute magnitude. Absolute magnitude. And again, it's independent of the sample size. Doesn't matter what the sample size. Cohen's D is the measure. All right. Cohen's D. Okay. So you have the difference, treatment versus non-treatment. So in this case, this is the treatment. This would be the non-treatment. Okay. So the 16 is, again, no difference. This is when we, again, introduce that red shirt. Okay. So what you would do is you're going to use your treatment, your population mean, and then you'll also use your standard deviation, that population standard deviation. So you have mean, you have your population mean, then you have standard deviation. Okay. All right. So then you would do, I'm doing it for this equation, for this sample, this study. I know that my mean difference is 0.09, 0.9, excuse me. Actually, I'll just write it in. So it's going to be 16.9 minus 16 all over 3. Okay. So then you get 0.9 divided by 3, which should give you, do the math. Point 0.9 divided by 3, 0.3. 0. So is this a small, medium, or large effect? It's small, yeah, small. But it is small, right? So these are the magnitudes. This is kind of the guidelines for the effect size measure. So from 0.2 to about 0.4, that's kind of a small effect size. You have 0.5 is medium, and then 0.8 is a large effect size. Let's increase this. So since all we're looking at is the mean difference at top, let's change this to 7.2. Okay. So now then we're going to use our second mean. First one. Second mean is 17.2. Okay. So now this is going to be 17.2. Which will be 1.2. 3.4. So as you increase the magnitude difference here, now you're able to see the actual effect, the magnitude of the effect of the Cohen's D. It's a standard measure of effect. Okay. How significant is that magnitude? Okay. If you again increase this a little bit more, you're going to increase your Cohen's D, you're going to increase your effect size. Right? The effect size is really affected by the mean difference and the standard deviation. Right? So if the standard deviation is smaller, then you're likely going to have a larger Cohen's D. Right? If the mean difference is larger, you're going to have a larger effect size. Okay. All right. Any questions about Cohen's D? So when they ask, what is the Cohen's, what is the effect size for the study, then you will use this formula. Use that formula with your Cohen's D. Right? So this is kind of an example. This is an SAT test. Okay. So first test there is a distribution of mean of 500 and a standard deviation of 100. Okay, so you have what a distribution of the sample. So say they took a distribution of whatever it is, they took a distribution. Now the new mean of the sample is 515, and the standard deviation is also 100. Okay, this is my point B. 0.15 is a small effect size, right? Okay, because again, 0.2 is small. So then the IQ scores, all right? So if you look at the magnitude, both of these 15-point differential in the core treatment and the opposite. This one also has a 15-point differential. So what is the difference? The difference is standard deviation. So the standard deviation for this one is 100, standard deviation for this one is 15. The magnitude is the same. The difference is the same. But we see that this is a very large effect size. It's very, very small. So now you're able to see what is affecting the effect size measurement. So again, the standard deviation plays a big role in the effect size as well. Okay. 15-point difference, two very, very different effect size measurements. One is very large, one is very small. Okay. Questions. And you also see just the magnitude graphically, pictorially, the difference. It's a very, very small difference. Much larger. Okay. Right. Question. First one says, increasing the sample size will also increase the effect size. Think about one. True, false. So if you're looking at this formula, you got treatment, population mean, you got standard deviation. And that formula or equation, rather, it doesn't have it in. So this point here affects is not affected at all by the sample size. It's only affected by this difference and standard deviation. Now, the standard deviation might be different based on your sample size, but we're not using the sample size or the standard error. We're using population standard. Okay? Now, if you use a larger sample size, like you saw here, now yeah, you will reduce this and you will increase this, but it has nothing to do with effect. Okay? Second, it says the larger difference between the sample and the population mean increases the effect size. That's very true. As you increase this up here, this number and this number are the same, you increase your effect size. We're good. Sample size is not affected. D, the mean difference in the numerator does. All right. This is the last thing we talked about today. Statistical power. Statistical. So, is we have to find the probability and what numbers we're going to need to reject the null hypothesis. We want to find a difference, right? That's the whole reason we do research. So when we do a power or a power test, we're looking to see how much our sample size needs to be, what our effect size needs to be, right? We're looking to see what those things need to be so that I can get a significant result, right? So power, that sub-bullet there says power is the probability that the test, a hypothesis test, will detect a treatment effect if one really exists, right? So that is the main reason we do a power test. We want to detect a treatment. We want to reject the hypothesis. Okay. Power is, again, like I talked about before, we usually do a power test before we do anything else to determine what our sample size needs to be, to determine what our effect size needs to be for us to get a significant result, to reject the no hypothesis. All right. There are three things we use and three factors that influence power. Three factors that influence power. They either improve it or reduce power. Your sample size, the size of the treatment effect or effect size, and your output. Those are three factors that influence the probability that you're going to detect a treatment effect that actually exists. So know those three: sample size of the effect, treatment effect, effect size, and then your output. Okay. Go all around here for types of type of there. Failing to reject no hypothesis, right? And then no hypothesis. So you're saying that it's a false positive. False positive. So you're saying that there is no difference in that. So there are three steps to calculating power. Three steps to calculating power. We're going to do it very quickly. Then we'll continue. Your power analysis. Probability that you're going to detect a treatment effect that actually exists. So the higher your power, greater the probability that you detect. What they mean by this. We go to the next one. Okay. So in this example, what they did was they have a no hypothesis with a population mean 8. Okay. And they said that alternative distribution is an N of 4 with an 8 effect. This is the new distribution. So you have the original distribution, the research. What regions will be those critical regions. So you got one with n equals 4, 7 times 4. That's the true hypothesis. That's the no hypothesis. True. And then you have one for the alternative. So population right. So now that's step one. Okay. And again, that's how they got 8 So they did square root, and this would be 10, this would be 4. And then over 2. All right. So the next step says locate the critical regions and compute the M critical. Okay. So if we're going to use a 5% significance level, we have to identify our critical region. All right. So we know that our critical region is using a 2-0. Plus minus 1. So name that there. All right. So then we need to identify that what is this critical region, right? What are the critical regions? So what is this? Say what? What looks like 90. Right? Slightly in front of them. So we define where 1.96 is. What is the value of 1.96? And the way we do that, here's the formula. So you're going to go M critical. You can see your null population, null plus C times the standard error of the mean. Okay. So what you're going to do, just going to plug your numbers in. So your first value is going to be the 8. Because again, this is my null hypothesis there. Population. You're going to do your Z, which is 1.96 times 5. You write me those numbers wrong. Okay. So all I'm doing is add add these two together. So you should get 1.95 times 5, 1.96. That should be 98 for now. 8 plus 9.8 should be 89. So that's my critical value. Okay. All right. Now, since I know that shaded region, I know this is my critical region. Now I have to find what proportion that shaded region is. Okay? I have to find that proportion. Okay. The way I do that is I have to do my Z formula. Right? So my Z formula is going to be M critical minus the alternative over the standard error of the mean. Okay? So all I'm doing is plugging values in. I have my criticals here, 89.8 minus 80. Oh, excuse me, 88. Okay, this is my alternative divided by 5. Okay, so then you get 1.8 divided by 5 should give you a plus 0.36. Okay. What do you do with 0.36? What do you think? What do you think you do with 0.36? What you would do with 0.36 is you go to your chart in the back. So if you have your sheet, you're gonna go find 0.36. Mm-hmm.
But what's
In the tail.
in 3, 5, 9, 4.
Right. So we got 4. So now it's 3, 5, 9, 4. With this information, what this tells me is with a 5 or 8 point difference and my n equals 4, that I have a 39, 35 point or a 36% chance of finding a significant result. That's the power of that study. Only 36%. Okay. 36%. So it's a 36% likelihood that I'm going to find a treatment effect that actually exists. Okay. Let's change one thing. So since I used an n equals 4 and I got this level of power, only 36%, let's change the sample size. Let's change it to, let's change it to 36. Okay. So now instead of being 4, we're going to change n 36. Okay. So now we're going to change everything up here. I'm just going to rewrite it here. We're going to use the same, everything remains the same, we're just changing the sample size. So it's going to be 10 over the square root of 36. 10 over 6 should be 1.67. Okay. Everything else will remain the same. A slide for this. Now we have to change this to 1.67. Okay. This will change. That will change. That will change. That will change. This will change. We know this is 1.67 now. 7. Okay. 1.96 times 1.67. 0.16 times 1.63 equals 3.7 plus 3 this 3 this should be 0.27, 83.27 minus 88. That's going to be negative 4.73 divided by 0.67. So now my z-score has changed significantly. Right? So if you were to go into the back of the book, your power should change significantly. Okay? Let me. Mhm. Yep. Let me see. Actually, I'm looking at it. So that one was, it should be, so if this one was 2 points, let me go to it myself. 2 points. Looking at that. Oh, you're looking at, so if it's negative, you'll be looking at the bottom. Let me check. So now, 39%. Um, 6% I use, I'm going to find 2%. How is this? It's not. It's a 8-point differential, 8-point effect, and a 36%, 36-point sample. Okay. So the power is showing this likelihood. And so what we would do is, if I wanted to determine how much I needed in my sample size, I would just play around with the numbers. Right? So we start off with 4, and it gave us this power. That's not a really good power. So I was like, no, let me increase it. Right? Let me increase it to 36. So I'm hypothesizing what will happen. Okay. And so now I got a sure thing with 99.77%, pretty much 100% chance to find something. Okay. Out. Out. All right. Shows you that that's the calculated power. So it showed you that. That's good. Okay. Here are ways to increase power, and here are ways to decrease power. These are really important. Okay. There are 3 ways. You can increase power by increasing the effect size. Right? So we talked about the effect size. How large is that difference? By increasing the sample size. Right? So we saw if we went from sample size of 4 to sample size of 36, we increase the level of power. Okay. And then you can also increase it by using a 1-tail test versus a 2-tail test. So you want to increase your power, you're going to use a 1-tail test. Okay. All right. Relative to a 2-tail. Ways to decrease power. You reduce the alpha level. So you go from, say, 5% significance level to a 1% significance level. By doing that, you're reducing the likelihood that you're going to find something significant. Okay? Or It's the opposite of what we saw in that third sub bullet point for increased power. You just use a two-cell test instead of a one-cell test. Okay, so those are ways to increase and decrease power. I like to think of power as schematic versus a microscope. Okay? Microscope can see very, very detailed, especially depending on how powerful it is. It can see down to the almost to the molecular level. Okay? If I go buy one from Walmart, not so much, right? If I buy one from, if I go in here into one of these labs and they have a microscope, I know for certain how it will allow me to see differences and again microscopic things. Okay, so the power is extremely important to be able to see those differences. All right, I think that is it for how we did all this. Yeah. So it says power of statistical test is the probability of the should be rejecting a false null hypothesis. Should be rejecting a false null hypothesis. Right? Any questions? Any questions at all? That's chapter 8. We want to give you this point. Um, it doesn't have to be due on Sunday. Just get it done. Just get it done. Go ahead. The last exam. That's a good question. I've seen exactly what the exam said. But it will be at home final, open book, open notes. Just get it done. No, we're not going to be here. We're off the entire team next week. Goodness. Alicia would. Yeah. Come through. No. Yeah. Yeah. Okay. That's all we got. Yeah. Happy Thanksgiving to you. Be safe if you're traveling. I'm already hungry. Ready. I'm ready to eat. Oh yeah. It's suspect. Yeah, yeah. Corona, man, you know, it's hit or miss. I can do it.
One person has the whole pay process. But like for holiday, it's the time. So I know a lot of things and like especially my business and rentability.
Love it. Love it. It's good. It's good. We're going to go out and say, enjoy your family. Thank you. Thank you. All right. Thank you. It's good. It's good. Oh, yeah. It's good. It's good. Be grateful. There's a lot of people out here who don't have. All right. Oh, it's all fun. It's good to get back.
Yeah.
Yeah, absolutely. You're just summarizing. That's it. Yeah, you're just summarizing. And so in your paper, they look at differences between groups, right? Yeah, so that's what you're describing. So what we're doing right now, we're looking at differences, right? And so you'll do a lot. So on the week coming back, I'll go over t-test. And so I think in your study they did an F test or a NOVA. We're not going to get to the NOVA, but you will know about a t-test, which is looking at the differences. And so you'll be able to explain what they're doing. Okay. And all you have to do is identify what the statistic is, and then it kind of explain what they use that statistic for. Because we both know, I mean, like I read it. I think it's in the note. So looking at various groups, looking at the differences. Which we kind of study this.